Today we're going to learn about endurance limit modifiers. Now the rotating beam endurance limit, SE prime, is usually known. In fact, most often it's either given to us in a problem statement or we're told the material we're studying and we can look it up in the appendix, look it up in tables. But the endurance limit modifiers are used to help us find the actual endurance limit of a part under specific conditions. So our real component's endurance limit. Now let's learn about this idea. The actual endurance limit of a part, SE, is equal to a number of modification factors times our unmodified or our rotating beam endurance limit. And so we need to solve for the factors that are specific to our problem or our part in order to find the real endurance limit of our specific geometry. Now, some of the factors that we have are things like the surface factor, defining how rough or smooth a surface is. The size factor, defining how large or small our part is. The load factor, defining are we loading in tension, torsion, or bending. The temperature factor, what's the temperature of our actual part? The reliability factor, how much reliability do we want? Do we want 50% reliability, 99% reliability, less reliability? And then there are miscellaneous factors that can be specific to certain conditions of our part that aren't usual, such as say there's a corrosion factor or a irradiation factor or something that comes into play. But ultimately, we need to determine these factors for our actual part so we can find that actual endurance limit. And let's remember that the SE prime, our rotating beam endurance limit, is usually known coming from tables. Now, what is the effect of finding this SE, this actual endurance limit? Well, when we look at our stress life curve and we consider that the curve is commonly representative of our rotating beam completely reverse condition, when we apply our factors, our K factors, to our actual part, we in essence are knocking down the endurance limit. We're saying that there is less stress amplitude over which we have infinite life, that our material is actually weaker when we consider its actual conditions, elevated temperature, certain surfaces, certain loading conditions, right? And so by applying these factors, we can get a more realistic understanding of its resistance to an applied stress amplitude and what the corresponding cycles to failure are. So now let's go ahead and learn about our first endurance limit modification factor. That is our surface factor. And let's just start with a picture here. We've got a picture of a part. One of them is unfinished, so it looks to have a rough surface. And another is polished and finished and smooth. Which of these two components will have better fatigue resistance? Now, if you selected the part that is smooth, then you selected the part that has more fatigue resistance. If you selected the part that has an unfinished surface, you selected the part that has less fatigue resistance. You see, smooth surfaces that have less defects on their surfaces tend to have better fatigue resistance. You see, stresses tend to be high at the surface of parts. And surface finish has an impact on the initiation of cracks. For example, let's look at a part that has a rough surface finish. Well, perhaps we're seeing tool marks. This part has been machined, so we're seeing tool marks going across the surface. If we think about this on the macro scale, don't each of these features represent a stress concentration? So rough surfaces, the more rough they are, the more stress concentrations exist on the surface, and the easier it is for a crack to initiate and grow from that surface into your part, knocking down its fatigue resistance. So then how do we incorporate this surface factor into the design of our parts? Well, the surface factor is a function of ultimate tensile strength, and higher strengths are more sensitive to rough surfaces. If we were to look at different types of machined surfaces as forged, hot rolled, machined or cold drawn, ground and polished, we can find the surface factor, Ka, versus the ultimate tensile strength. And we can see the more strength that a part has, the more of a knockdown on that surface factor, the lower our resulting endurance limit will be. But we also notice that if we have a finely, nicely polished part, that the surface factor has almost no impact, telling us that whenever possible, if we're making parts, we should be polishing them. We should be removing any roughness or notches or edges on its surface to give it as much fatigue resistance as possible. So then how do we apply this surface factor in design? Well, the surface factor Ka is equal to A, a material constant, times the ultimate tensile strength to the power B, a material constant, where for different surface finishes, as listed in table 6.2, we have different values of the factor A and the exponent B. And let's note that if we're using KSI units, we'll need a certain A factor, and if we're using megapascal or metric units, we have a different A factor for the difference in the units. Okay, now let's look at our next modification factor. And this one is our size factor. The question here is, which part will have better fatigue resistance? A part with a small diameter that has a smaller circumference and less surface area available for defects, or a part with a big diameter that has a bigger circumference and a larger surface area for defects? Which part will have better fatigue resistance? If you selected the small diameter part that has a smaller diameter, less circumference, and less surface area for defects, then you have selected the correct answer. Smaller parts have better fatigue resistance up to a limit, right? And why? Because large parts have larger surface areas with more potential sites for defects. And the likelihood of crack initiation becomes higher because there's more defects. The size factor is obtained from experimental data that exhibits a wide amount of scatter. Now let's apply this size factor. Let's first note that for axially loaded parts that are loaded in axial direction, there is no size effect. We set that KB value equal to 1 because when we are loading axially, the entire cross-section is being given the equal opportunity for crack initiation. Now the next thing we need to note is there's a couple of special conditions we're going to have to test out. One of the things is if our part is round or rectangular. Another set of conditions is if our part is rotating or if it's non-rotating. Each of these conditions gives us a different size factor equation that we're going to have to use. It's a little bit complicated, but the main thing is for us to look for round, rectangular, rotating, non-rotating. Let's start with a part that is round and rotating, subject to bending and or torsion. So it's round and we are rotating it. It's spinning around, right? In that case, the size factor KB is equal to these inequalities, where if the diameter is between 0.3 and 2 inches, 2 inches and 10, or 7.62 and 51 millimeters, 51 millimeters and 254 millimeters, then we simply put in the diameter of our part in the given units with these power exponents to calculate a KB term. So if it's round and rotating, what's the diameter? Choose one of these and apply it. Be straightforward. Now let's consider a case where we have a part that is round and non-rotating. So it's round, but it's not rotating. Maybe it's just bending, but it's not spinning around. In that case, we are going to replace the diameter with an effective diameter DE, where DE is equal to 0.37 times the actual diameter. And once we do that, we go ahead and plug that DE in to our original set of equations. We find where we are, and we get our KB value using that effective diameter instead of the actual diameter. And then another condition, what if we have a rectangular part that is non-rotating? A rectangular part that's non-rotating, we'll set the effective diameter is equal to 0.808 times the height times the base, the square root of those two terms. We'll then take that effective diameter, replace D, and again, search in our inequalities and calculate our KB value, right? So there we go. Now we've got our size factor. Now let's find our load factor. And the question here is, for the load factor, which part will have better fatigue resistance? Let's consider the case of a part that has uniaxial bending. So we're bending in one direction, we're unloading. Let's consider the case of a part that has reverse bending. We're bending back and forth, up and down, up and down. And then let's consider the case of rotating bending, where we have it bent and we are spinning our part. It is a rotating part. Which of these scenarios do we think will have better fatigue resistance? Let's also kind of think about crack propagation. The more stable crack propagation we have, the more cycles of failure we'll likely have. So bending, where a single edge or point is subject to maximum minimum loading in the structure, is the case where we'll have more cycles to failure. And in our case, that is the rotating bending scenario. The classic Euler experiment is where we're going to have more fatigue resistance. Because when we are rotating that part that is bent, there was a single point along that sample at any particular time that's subject to the maximum and the minimum loading condition. Now, what does this loading factor account for? It accounts for the stress distribution across the cross-section. It accounts for changes in the endurance limit due to the type of loading. It's only to be used for a single type of loading, not combined loading. And if we do have combined loading, well, we're going to learn later on how do we deal with those combined loading conditions and fatigue resistance. Now, the beauty of the loading factor is it's actually pretty simple for us to apply, with a load factor Kc is equal to 1 for bending, 0.85 for axial loading, and 0.59 for torsion, where torsion gives us the biggest knockdown on our endurance limit. Okay, now let's move on to our temperature factor, right? And here we have two scenarios. We have a part subject to fatigue at room temperature, and we have a part subject to fatigue at high temperature, to the point where the sample is glowing inside of the furnace. Which part will have better fatigue resistance? A part that's at room temperature or a part that is hot? If you selected the part that is at room temperature, then you are correct. The part that is room temperature has higher fatigue resistance. You see, at high temperature, the endurance limit of a material decreases, and sometimes it can even disappear, even for alloys like steel, such that the fatigue strength or stress amplitude to failure decreases or declines. So how do we incorporate the effect of temperature into our endurance limit? Well, for steels, what we can simply do is replace the room temperature strength, the room temperature ultimate tensile strength, with the elevated temperature strength, the strength at a targeted temperature, where given a polynomial in Fahrenheit or a polynomial in degrees Celsius, we can simply put in the temperature that we know, put in our room temperature strength, and determine our target temperature, the elevated temperature strength. And then we can just use that strength everywhere throughout our problem. Now, the temperature factor is simply that ratio of the target temperature over the room temperature strength. How do we use it? Well, first we calculate the KD, and then we can find ST, our target temperature strength. And if we know the room temperature endurance limit, we can use the KD to find the actual endurance limit at temperature. Now, an important thing we do have to note for temperature is that temperature, since it is modifying the strength of our part, also modifies our S1000 point, where we've got to put that F value times the, where the strength at temperature times our F factor gives us our S1000. So when we look at our stress life curve at elevated temperature, not only are we knocking down the endurance limit, but we're also knocking down the position of S1000. So we can have a lot less strength at elevated temperature, right? Okay, now let's look at our reliability factor. Now, when we plot the rotating beam endurance limit versus tensile strength, we see a lot of scatter in the data. And we saw this earlier, where the endurance limit versus the tensile strength on average has a 50% relationship. But it could range between as low as 40 and as great as a 60% relationship. What this means is whenever we're using the 50% value on tensile strength, whenever we're using this value, we're only representing 50% reliability of what the endurance limit is. But the reality is, and so that means we're just trying to fit the middle of the scatter in the data, 50% reliability. Where in reality, we could be as low as this, or we could be as high as that on our stress life curve. So how do we then try to incorporate reliability and shift our curve so we can have more reliability or less reliability in our design? Well, what we can do is introduce the reliability factor, KE, where KE is equal to 1 minus 0.08 times ZA, where 0.08 represents 8% standard deviation of the endurance limit, and ZA is a transformation variant. If we then go to table 6.4, we can select a reliability, find its appropriate transformation variant, and actually even be given directly the reliability factor for the ones that are in this table. So now we can say, I want a design that's 99.99% reliable, meaning I don't want this part to have any potential of failing. Well, then I'm going to have a much more restrictive endurance limit to play with. And now finally, our miscellaneous factors. There exist many conditions that can modify our endurance limit. And the miscellaneous factor exists to remind us that these conditions should be incorporated into our design process. The value of KF is not always available. In some cases, we may not have experiments. We may not have enough data. We may not have the hundreds of experiments that help us to define it. And additional experiments may be required to characterize the behavior. Some examples of factors are things like residual stresses or as-built defects in additive manufacturing. Things like directional characteristics of the microstructure. In 3D printing and metal 3D printing, you can have elongated grains that change the strength depending on how you're loading your part. Some materials have poor corrosion resistance. And so if they're in a corrosive environment, and which lowers the barrier for surface defects, you can have a lot faster fatigue, crack growth, and failure. Things such as surface condition. Say you have a part and you've electroplated it, you've metal sprayed it, you've shot peened it to try to give it more surface hardness or applied coatings. Those can change the fatigue resistance. Cyclic frequency. If you're loading very slowly or you're loading very fast, that can change the response of a material to fatigue. Fretage corrosion, where parts are rubbing and wearing against each other. Or even things like radiation, where high fluence of different forms of radiation are knocking elements out of out of the atomic structure of your part and transmuting elements and leading to a degradation of the entire microstructure of your material. Overall, as a design engineer, we must be careful to think about the environment and the conditions in our design and how they might affect our fatigue resistance. And if and try to identify appropriate modification factors for that design. And of course, if KE is not given to you, and if you find no additional factors are necessary or information is available for them, then you can simply set KE equal to 1. And in most cases in this course, we would set it equal to 1. So now at this point, we've covered all of the basic endurance limit modification factors. We know how to apply each of those factors. And once we've calculated them for our specific geometry, we can then multiply them by each other in our unmodified rotating beam endurance limit to get the actual endurance limit of our part under its specific conditions.